Well, hello, friends. Hope you're ready for some more mathematical, astronomical excitement. Because now we're going to talk about Newton's version of Kepler's third law and how to calculate through that. Newton was able to insert his idea of gravity and mass and account for Kepler's missing constant that would explain why a planet's orbits were the length and time they were. Amazing stuff. So, again, just for clarity's sake, this is the formula here. P squared equals 4 pi squared a cubed divided by G, big G, times M1 plus M2. That's it. P is your orbital period. A is your semi-major axis. M is the mass of the first body. M2 is the mass of the second body. And G, of course, big G, is equal to 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. Always. That's why it's a constant. So now, in this first question on these practice problems, they ask you to rearrange this formula to solve for the first mass. Now, here was the great thing about Newton's version of this law, was that we could use it to back calculate masses once we knew orbital period. And he was the first one to estimate the mass of the sun this way. And highly accurately, might I add. Okay, so now let's just rearrange this real quick. And this is just algebraic rearrangement. So you say P squared, always again, start with the original formula. When in doubt, when feeling confusion, when in danger, when in doubt, don't run in circles or scream and shout. Just start with the original formula. And what we want is the first mass by itself. So in order to, here, come in a little closer, friends. In order to find the first mass by itself, we have to start getting things separated. So we're going to multiply both sides by what's beneath our fraction here. G times M1 plus M2. And because we do it to one side of the equation, we have to do it to the other. So G times M1 plus M2. Here they cancel. So now we're left with G M1 plus M2. So you're adding the masses in this formula. Times P squared is equal to 4 pi squared a cubed. So now, in order to get the mass by itself, we're just going to divide both sides by G P squared. And it's always better, always do this with these simple letters before you start trying to put these ginormous, long, weird scientific notation numbers into it. Get your formula set and then put your numbers in. Trust. Again, things I've learned the hard way. Let me save you some pain and effort, friends. So over here, G cancels G and P squared cancels P squared. So we end up with M1 plus M2 is equal to 4 pi squared a cubed divided by G P squared. Now, I know that looks complicated, but it's just letters. I mean, yeah, there's a Greek letter and one number, but it's not that really. You just keep rearranging it. Now, in order to get M1 by itself, we subtract M2 from both sides. Because if we do it to this side of the equation, we got to do it to this side too. So then our final answer would be M1 is equal to 4 pi squared a cubed divided by P squared. Go ahead and just put all that in parentheses, minus M2. Easy peasy. Nothing to it, really. So let's try and walk through one of these equations and see how we do that, huh? A little trickier. Let's look at number 7, where it says, given the following information, calculate the orbital period. So again, here, with a hand, which I had to move for this, and let's come down here. Yeah, are we having fun? Are we having fun? Are we? I am. I like this stuff, though. Wait, are you centered? Are you comfortable yet? Will that work? Can you see everything over here now? on the magic whiteboard? Okay. Can you tell it's the end of the day and I'm tired? Getting kind of wacky. All right, here we go. So number 7 asks to calculate the orbital period. And we're going to calculate it in seconds. I think I can give it to you in seconds. So for number 7, it says p squared, again, always start with the original formula, is equal to 4 pi squared a cubed divided by g m1 plus m2. Yes? Yes. But we want p by itself. We want to know the orbital period. So we have to take the square root of p squared and the square root, because we did it to one side of the equation, we have to do it to the other, of 4 pi squared a cubed divided by g m1 plus m2. These cancel. The square root will cancel the square. They're the opposites of each other. And we end up with p equals the square root of 4 pi squared a cubed over g m1 plus m2. There's your formula. Here's the one you're going to use right here, baby. Here it is. Got it? So now we take our numbers. We got g, of course. And we have the mass of the first object, which was equal to 4 times 10 to the 5th kilograms. Play it with 4 a little bit. And then m2, which is equal to 2.1 times 10 to the 4th kilograms. And you have a semi-major axis, A, of 2,000 kilometers. And of course, big G, which is equal to 6.67 times 10 to the negative 11th meters cubed per kilograms second squared. I might suggest, if you haven't started to already, memorizing this constant. It's everywhere. It's what makes it constant. Yeah, memorize that. All right. So again, note this is in meters. This is in kilometers. Just multiply by 1,000. 1,000 meters per kilometer. Kilometers cancel, of course. And you get 2,000 plus 3 zeros, or 2 million meters. Now we just plug all that stuff into our equation and say P equals the square root of 4 pi squared times 2 times 10 to the 6, or million meters cubed, divided by 6.67 times 10 to the negative 11th meters cubed per kilogram second squared, times 4 times 10 to the 5th kilograms plus 2.1 times 10 to the 4th kilograms. Run this line out. And we take the square root of all that. Yes? Cool, isn't it? So then we say P is equal to the square root. And now we just start calculating this stuff out. 4 pi squared. And you take the cube of that, and you get 8 times 10 to the 18th meters cubed. Because remember, that's like taking meters times meters times meters. All your units get cubed and squared right along with it. That's how we keep track of it all. And I always wait for big G to calculate big G until I have the masses added together. Always, when in doubt, do it step by step. It will help you in the long run. It will help you think about it better, and you'll just become more efficient at thinking this way. Trust me, it's really worth it in the long run. So then we add these masses together. Oh, wait, which one am I looking at? Okay, here I am. My bad. And we get, well, this is easy, 421,000 kilograms. Did you see that? That marker tried to attack me. Not that I'm tired and slipping at the end of the day since I've been here since 7 a.m. and it's after 5. Hang tough. We're going to get through all this together. So then I would multiply these and multiply these. Now, again, this is one number. Think of this as a single number. Put that in your calculator with parentheses around it. It'll help you. So then we get P is equal to the square root of, where do I have my paper? Where am I? 3, and I hope that's why you're getting 2 as you're working through this, 0.158,273,408 times 10 to the 20th meters cubed over, multiply these two together. This is a crazy looking number. I got 0.00028,081 meters cubed per kilogram second squared. Where did I lose my kilograms? Oh yeah, watch this. Watch this. These kilograms cancel here. Because this one's below the fraction, this one's above. Here, look at this. Our meters cancel. And this one doesn't even exist. All we're left with is seconds squared. So, and because we want our period, our orbital period, how long it takes to be in time, that makes sense. That's really good proof that we're on to the right answer here, guys. So just stick with it. Oh, this video is getting real long. So we divide those out. We get P is equal to the square root of 1.124701189 times 10 to the 25th seconds squared. Take the square root of that, and you get an orbital period of 3.353656495 times 10 to the 12th seconds, because of course it's the square root. It'll kill that square. Boom. It's gone. So there you go. That's how long it would take this object with this mass, this object with this mass to orbit this object with this mass at this distance. There you go. That's quite a bit of time, actually. So keep working on these. Email me with questions. And of course, keep looking up.